This video is on areas and definite integrals. In the previous video, we actually talked about finding the area under a function using rectangles. And we used Riemann sums with a left-hand sum and a right-hand sum. And basically, the more rectangles you use, the more accurate your answer could be for the area under the curve. So, what we know from that is that for our area, it's equal to, if I write this as, what if I used an infinite number of rectangles? It's equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Remember, this was how we found the rectangles, and then we were adding them all up. This means take the sum of them. If we used n rectangles, you're adding up n rectangles. If this had an area, with a height and a width for each of them individually as you iterated I from 1 to n. If I take the limit as n goes to infinity, what I'm really saying is use more and more rectangles. The delta x would get smaller then, right? Because that'd be the width, that delta x is equal to b minus a over n. So delta x would get smaller, which means that we'd fill in more of the area. And if we use an infinite number of rectangles, we'll get the exact area under the curve. So that's really what's going on when we find area. We're not going to really use this, but just have an understanding of what I'm talking about there. Let's just look at a couple examples. If I said for f of x equals 5, find the exact area under the curve between x equals 0 and x equals 4. If I was to do that, let's talk about what this would look like just as a picture, right? So we'll use geometry to help us here. Here's our x-axis, here's our y-axis. If I say f of x equals 5, I'm talking about 1, 2, 3, 4, 5 would be here. And the line f of x equals 5 is the same as y equals 5. So it's really just going to be, right, this line here. That's f of x equals 5, because y equals 5 is a horizontal line. And we want to know between x equals 0 and 1, 2, 3, 4, what the area under the curve is. Well, it's easy enough to think to yourself, okay, I'm going up to here, I'm looking for this area. Well, how would I find that area? Well, area is equal to length times width. In this case, we've got this height of 5 times this width of 4. So we have 5 times 4, which equals 20. And, since I didn't give you units, we'll just say it's square units. Remember, units of area are always squared. So if you can find the area using geometry, it works out kind of nice, like we just did here. We had a rectangle, so it was pretty obvious. We'll look at one more like that, and we'll talk about how we can use the derivatives, or the antiderivatives, sorry, to find the area under a curve. So let's look at one more. If I said for f of x equals 2x, find the area under the curve between x equals 0 and x equals 3. Well, if I was looking at this, let's take a look at what the sketch would look like. So we got an x-axis, we've got a y-axis, go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Let's graph f of x equals 2x. Well, that's the line y equals 2x. So the y-intercept would be 0, right? 0, 0. And the slope will tell you to go up 2 over 1, so I'd go up 2 over 1. And you want to be accurate, so you would do a few of these, up 2 over 1, up 1, 2 over 1. And then this would be our function, right? So this is f of x equals 2x. Now we want the area from between 0 and 3. So here's 3. So we're going to go up here and we're looking for this area. Well, what shape do we have? We have this triangle, right? And the area of a triangle, if you remember, is equal to the base times height divided by 2, or 1/2 base times height. They mean the same thing. And we're really just looking at evaluating this. Well, this is 1/2. What's the base? Well, the base is 3. So 1/2 times 3 times what's the height? Well, it's the function value, right, at 3 for f of x equals 2x. So f of 3 equals 2 times 3, which equals 6. So the height is going to be 6. And then we're multiplying together. 1/2 times 3 times 6. 3 times 6 would give you 18, divided by 2 is 9. This is 9, again, square units. So the area under this graph, right, between 0 and 3 is 9 square units. Now, in both these cases, we were fortunate enough to use geometry for formulas that we already knew the area of to be able to get the area under the curve. That won't always be the case. In the last section, we saw how we did that using rectangles, right? In this section, we're going to talk about how the definite integral will help us get there. So we'll do a little definition here first, and then we'll go back to talking about finding area under the curves. So to find the area under a non-negative, this is important, right? So under a non-negative continuous function f, right? So over a non-negative continuous function f over some interval from a to b. So when I say non-negative, I'm really saying that the y values are all 0 or positive, so it's all above the axis. In other words, all above the x-axis. This is what I mean about non-negative, right? A closed interval from a to b, you know, those are the endpoints. First thing you want to do is find what I'll call capital f of x, the antiderivative of f of x. So you find the antiderivative, and then the second thing you do is you evaluate f of x using what we say f of b minus f of a. In other words, you substitute in the endpoints and you take the difference, you subtract. You always substitute in the right endpoint first, subtracting off the left. So f of b minus f of a. And this is the area under the curve f of x on the interval from a to b. Right, so whatever you get as your result there, that would be the area. Now, we can kind of see this with the last example, just taking a look at what we had. Remember the last example, we had f of x equals 2 to x, or equals 2x, and we said find the area under the curve from x equals 0 to x equals 3. And, you know, we just did it. I'm not going to sketch it again. We knew it was a line y equals 2x, but even if we didn't know that at this point, as long as f of x equals 2x is positive or non-negative on this interval from 0 to 3, we're okay. And in this case, we are going to be positive, right? 2 times 0 will give you 0 there. 2 times 3 will give you 6, and everything in between would all be positive. So we know we're non-negative. But let's just find what capital F of x would be here. Capital F of x, we took the antiderivative of 2x. Well, remember how it works. 2 can stay in front. The antiderivative of x will be add 1 to the exponent, so it's x to the second power, and then divide by that same new exponent, so divide by 2, plus c. And here we see that the 2's will cancel, and we end up with x squared plus c. So that's what f of x is equal to. So if I said f of b minus f of a, right, the interval is from 0 to 3, so it's like a and b. So f of b is f of 3 minus, maybe I'll write this as area equals, so you know that's what I'm finding. Right, so area equals, according to what this formula tells us, f of b minus f of a is f of 3 minus f of 0. And substituting that into here, right, f of 3 is going to be 3 squared plus c, minus f of 0 would be, in parentheses, 0 squared plus c. Well, what's this equal? 3 squared will be 9. So 9 plus c. Here you have to distribute the negative sign through. 0 squared is just going to be 0. Negative 0 is just 0, so that's going to be 0. Negative times the positive makes us negative c, so this equals 9, and that's 9 square units. It's the same area we actually just got on the previous page. Just to show you, right, 9 square units using geometry. But here we used the antiderivative of our function. We're allowed to do that as long as our curve is positive or non-negative over the interval that they gave us from 0 to 3. So let me give you another definition here, and this is going to be the definition for the definite integral. So it's really kind of like what we just did. It'll actually be a little more succinct, but we'll write it out. So this definition here. I'm going to say let f be continuous over the interval from a to b, and we'll say capital F be any antiderivative of f. Right, so capital F is the antiderivative of f. Then the what we call definite integral of f from a to b is, that's the definite integral of f from a to b, and it's given by, right, take the antiderivative of, right, the integral. Now this time, before we've seen indefinite integrals where we didn't have this interval from a to b. Here we do. So it goes from a to b. So this is the definite integral, right, from a to b of f of x dx. That's how you write it. A and b here are called your limits of integration. All right, it's not a limit like finding the limit. They just call these the limits of integration. It just means the endpoints that you're going to be using. So definite integral is the integral from a to b of f of x dx, and it's equal to, take the antiderivative and sub in b, so it'd be capital F of b, minus taking the antiderivative and subbing in a, so it's capital F of a. So it's kind of like what we said above, right? F of b minus f of a. All I'm saying is this is kind of the form we're using when we take the definite integral from a to b of the function f of x dx. You find the antiderivative and then you sub in b, you subtract off subbing in a. Now if this f of x, right, our original function that we're taking the integral of, is non-negative, that's equivalent to the area under the curve. That's what we wrote above. So I'll just write it out here again just so you see it. So for a non-negative function, right, so for a non-negative function f of x, This is the area under the curve. So, this will always give you something that you can evaluate as long as the function doesn't have limits of integration that are, at infinity or where the function is not defined. But the definite integral here, when you evaluate it, will only give you the area under the curve if it's a non-negative function f of x to start with. If it isn't a non-negative function, meaning if f of x goes below the axis at all, you still can evaluate this. It's just not equivalent to the area under the curve. It would be equivalent to the net change, and we'll talk about that a little bit later. Let's do some examples using this. All right, so this is really how we're going to find area going forward. We're going to use the definite integral, the antiderivative, to help us out here. So for this example, if I said find the area under f of x equals x to the third power plus 2 on the interval from 2 to 4. So first off, to find the area, I kind of want to make sure this is a non-negative curve. For f of x equals x to the third plus 2, on the interval from 2 to 4, 2 cubed, that'd be an 8 plus 2, that's positive. 4 cubed, that's going to be 64 plus 2, that's positive. And then everything in between there will be positive. You can kind of see that because, to make this negative, the x values here, would have to come out to something negative and also larger than 2 when you cube it. So we know it's going to be positive, but if you're not sure, you just do a quick little sketch of this. You don't have to sketch this, but it might help you see what's going on. If we had an x and y axis here, x cubed plus 2, you should know what a cubic function looks like. Plus 2 means you're being shifted up 2 units, so here's 2 here. And it would look something like, I'll draw it in red, it would look something like this. Alright, so this is our f of x equals x cubed plus 2. I want to find the area under the curve between 2 and 4, so 1, 2, 3, 4. What I'm really looking at when I'm talking about the area here is this area here. Now, in the previous section, we would have said, okay, let's use so many rectangles to try to find that area because we have a curve. But because we're using rectangles, we weren't being accurate. We're either going above a curve or below the curve, depending on if we use left-hand rectangles, right-hand rectangles for the endpoints. But in this case, we're going to use the antiderivative, right, of the definite integral to make sure we get the exact answer. So our solution here, all right, we have a positive curve, so we can take the antiderivative on what interval? Well, from 2 to 4. This is our a to b, so from 2 to 4 of f of x, which is the x cubed plus 2, and then dx at the end. Now, once I do this, you evaluate the antiderivative first. You don't substitute in first. So evaluating the antiderivative right away, I'll do this in brackets here. X to the third power, remember you add 1 to the exponent, makes it x to the fourth, and divide by that same new exponent. So you get x to the fourth over 4, plus the antiderivative of 2. The antiderivative of a constant is just that constant times x, so we got 2x, because, it's just with respect to x. And now we don't put plus c here, and I'll explain why in a minute. But you don't need plus c for a definite integral. If it has limits of integration, you don't need the plus c. If it didn't have the limits of integration, then you would put plus c like we had in the past for indefinite integrals. But then we're going to put the limits of integration on this far right end, so from 2 to 4. Sometimes you'll see a bar here at the end with 2 to 4, but make sure you understand that the integral symbol is gone now, the dx is gone, because you've taken the antiderivative. Now, according to how we wrote our definition, we don't really talk about it this way, but just so you realize it, this is like that capital f of x we were talking about down here. The antiderivative of f was this capital F. right? So the antiderivative of f was the capital F, and that's what we're talking about. So we found f. So this is f of x, and then what you do is, we said we want to do f of b minus f of a. So what you're really doing here is you're taking this and you're subbing in f of 4, right, minus f of 2, subbing in 2. So first you sub in 4, subtract off subbing in 2. That's really what you're doing. So x to the 4th over 4 plus 2x, subbing in 4 would be 4 to the 4th over 4 plus 2 times 4. This is me doing the first part, f of b, minus subbing in 2 into here. Alright, this is the f of a according to our definition, right? F of b minus f of a. F of b was f of 4, subbing in 4, minus f of a is subbing in 2. So we would have 2 to the 4th over 4 plus 2 times 2, because we're subbing 2 whenever we saw an x. And then you evaluate this. And evaluating this, 4 to the 4th divided by 4, you can cancel one of the 4's really, and get 4 to the 3rd power, which is 64, plus 2 times 4, which is 8. There's nothing to distribute through here, so you can drop those parentheses right now. Minus, here we have, inside these parentheses, you have 2 to the 4th, which is 16 divided by 4, which gives me 4, plus 2 times 2, which is 4. And this gives me 64 plus 8 gives me 72, minus 4 plus 4. You could actually add these. You could also distribute and then add them. It's either way is the same. 4 plus 4 gives you 8, so this is 72 minus just 8. I can drop the parentheses because 8 is the only term there. And then 72 minus 8, well, that's equal to 64. And then what are the units on this? We don't give you units. We just say it's square units, right? It's the units of area, because we know we're trying to find the area under the curve. All right, so we don't put square units every time, but if we're talking about area, we would. And then you have it. Now, when you took the integral up here, when you evaluated the antiderivative here for x cubed plus 2, usually you'd put a plus c at the end. The reason we didn't put plus c here is that unknown constant, no matter what it is, if I put plus c here, I would have had a plus c here and a plus c here when I substituted back into this, and then the c minus c would always cancel out. So those unknown constants actually don't really matter when you're doing a definite integral, because they cancel out with one another. So that's why we don't put c into the problem. It's kind of like when I showed this in this small instructive example here, right? These c's ended up canceling. That'll always be the case. So we don't actually put a plus c when we're doing a definite integral. Let's take a look at a few more. If I said to evaluate, so that was looking at the area under the curve. Sometimes you'll just be asked to evaluate the definite integral, and you do the same thing. It's just a matter of understanding that it's not always going to be the area under the curve if it's not over a positive value. So if it doesn't say the area under the curve, we're not going to even talk about the units being squared. But if I said to evaluate this integral from 1 to 4 of x squared plus 2x plus 1 dx. Alright, so we're just going to evaluate this. I'm not asking you about the area right now. I'm just going to say, alright, let's take this antiderivative. Now, it would be equal to area under the curve as long as this function's non-negative between 1 and 4, which this parabola is, but we're just going to go through and evaluate this just to make sure we know how to take the definite integral. So, first thing here is, once you have this, you want to take the antiderivative. So, taking the antiderivative of the inside here, antiderivative of x squared would be x to the 3rd power. Remember, you add 1 to the power and then divide by that same new power, so it's x to the 3rd over 3, plus the antiderivative of 2x. Well, 2 is a constant in front. X will be x to the, you had the power of 1, you add 1, so it'll be x to the 2nd power. You divide by that same new power, so divided by 2. Plus the antiderivative of 1 is just going to be x, and we're going to evaluate this from 1 to 4. Remember, we don't put a plus c in here for a definite integral. Alright, and now we want to simplify this. These 2's are going to cancel with one another, so that second term is just x squared. And then what do? Well, remember what this actually said for us to do. We're going to take f of b, meaning subbing in the upper limit, and then subtract off subbing in the lower limit. The order matters. You have to do the top limit, the upper limit first, and then subtract off substituting in the lower limit. So substituting in, I would have, for the first part, subbing in 4, I'd have 4 to the third over 3, plus the 2's canceled here, so we just have 4 squared, plus subbing in for x, we get 4, minus, now we're going to substitute in 1. So 1 to the third over 3, plus 1 squared, plus 1. So we're subbing in 1 everywhere into the function here. And now it's just up to us to simplify. Simplifying this, the first set of parentheses you don't really need around this. There's nothing to distribute through it. So 4 to the third is 64 over 3. Keep it exact. All right, don't give me a decimal here. Plus 4 squared is 16 plus 4. Minus, inside these parentheses, I've got 1/3 plus 1 squared, which is 1 plus 1. And so I end up with 64 over 3 plus 16 plus 4 is going to be plus 20. You can combine those right now. Minus, here I've got, inside these parentheses, 1/3 plus 2. And I'll distribute this negative sign in. Since 2 and 1/3, right now I need a common denominator to add them. I'll just leave them and then we'll combine them in a minute. So 64 thirds plus 20 minus, we have 1/3, and then negative times a positive makes us a -2, right? Distribute the negative sign to both terms in there. Combine these like terms, I end up with 64 thirds minus 1/3. You might want to combine these first, gives you 63 thirds, plus 20 minus 2 will give us plus 18. 63 over 3 actually divides out evenly. 63 thirds is going to be 21. All right, 63 divided by 3 is 21, plus 18. And this equals 39. So the antiderivative here is equal to 39. It's the area under the curve, as long as this function is non-negative, but since we didn't ask about area, the answer is just 39. We evaluated the definite integral. All right, so let's take a look at just a few more. If I said to evaluate the definite integral from 0 to 6 of e to the 5x dx. So what you remember you always have to do first when taking this definite integral is actually take the antiderivative. All right, so you always take the antiderivative first. You never substitute the limits in before you take the antiderivative. So taking the antiderivative here, the antiderivative of e to the 5x, remember how it works. The antiderivative of e to 5x, you're going to write exactly what you see, and then you divide by whatever the constant was in front of x, right? So you divide by 5. So we got e to the 5x over 5, and we're going to evaluate this from 0 to 6. Make sure you don't write the integral symbol anymore. A lot of times people do that. That's incorrect. You know, you lose points for that. Once you've taken the antiderivative, we don't write the integration symbol anymore, and we don't write the dx anymore. So we've taken the antiderivative of e to the 5x over 5 is what we have, and we're evaluating it from 0 to 6. And remember what you do. You substitute in the upper limit first. So it's e to the 5 times 6 over 5 minus e to the 5 times, subbing in the lower limit, 5 times 0 over 5. And notice I didn't put parentheses around these because these are each one term, so you didn't really need it. And then we're going to evaluate, evaluating what we have here. E to the 5 times 6 is e to the 30 over 5 minus e to the 5 times 0. Well, what's e to the 5 times 0? It's really e to the 0, right? If I say e to the 5 times 0, that's e to the 0. What's e to the 0 equal? Well, e to the 0 equals 1. Remember, any base other than 0 to the power of 0 gives you 1, right? So if you see this as 0 power, you know it should be 1. So this is minus 1 over 5, just replacing that numerator with 1. And then we could write this, you could leave it like this, or you could write this as a single fraction. You already have a common denominator there. You could write this as e to the 30 minus, e to the 30 minus 1 all over 5. Alright, so either way, just keep in mind that we want the exact answer, which is what we found. This is also the exact answer here. But the point being is that this should be the exact answer. You don't want to give me a decimal approximation unless we ask you for it. A decimal approximation would be you typing e to the 30 in your calculator and then evaluating what this would be. We want the exact answer unless we ask you to approximate. And we'll look at maybe one more like this. So if I said take the antiderivative, right, so we're going to evaluate the antiderivative from 1 to 9 of the square root of x, and then plus 3, that plus 3 is on the outside of the square root, make sure you recognize that, dx. So first thing I want to do is take the antiderivative of this. And before I can take the antiderivative of the inside, remember I have to rewrite this. If I see any square roots or x's in the denominator, we want to rewrite this as x to a power so we can use our rule. So we're going to rewrite this. It's still the antiderivative because I'm not taking the integral yet. Make sure you're just rewriting. Never take the antiderivative while you're rewriting. So we're going to rewrite this as, this is x to the square root is what power? It's the 1/2 power. Alright, plus 3 dx. And then once you've done that, now let's take the antiderivative. So the antiderivative of the x to the 1/2, well, how do you find that? You add 1 to the power, so 1/2 plus 1 would give you 3/2, and then you divide by that same new exponent, so we divide by 3/2, right? That's our rule for when we integrate x to a power, right? You add 1 to the power and then divide by that same new power, and we'll simplify that in a second. Plus, this is 3, the antiderivative of 3 is going to be 3x because with respect to x. And then, remember, we want to evaluate this from 1 to 9. So again, we're going to put plus c there because it's a definite integral. And I'll simplify this first. So taking this, I'll just take it over here. It's easier to work with. X to the 3/2 over 3/2. Remember, when you divide by a fraction, you multiply by the reciprocal. So we multiply 2/3 times x to the 3/2. And if you saw it in this step, you could have just written it right away. I just wanted to make sure you understood what I did. So plus 3x, this is going to get evaluated between from 1 to 9. And then we will follow through with what we normally do. Substituting the upper limit, subtracting off, substituting in the lower limit. Alright, so first part will be 2/3 times x, which is now 9 to the 3/2, subbing in the 9 first, plus 3 times 9, make sure you sub 9 into the whole thing before you start the next part, minus, and then we're going to substitute in, make sure you put parentheses around it, substituting the lower limit, which is 1. So we have 2/3 times 1 to the 3/2 plus 3 times 1. And then this is equal to, let's simplify it. This is going to be 2/3 times, just looking at this first part, 9 to the 3/2. You have to remember what these rational exponents mean, right? The 3 over 2, the 2 in the denominator means take the square root, right, and then raise it to the 3rd power. So if I was taking the square root of 9, that would be 3, and then 3 to the 3rd power would be 27. So this is 2/3 times 27 here. You should know how to evaluate that. Plus 3 times 9, which is 27. And we can close off that first set of parentheses, minus the second set of parentheses here. 2/3 times 1 to the 3/2, or 1 to the 3/2, that's just going to be 1. Because 1 to any power is going to give us 1. So then we're just left with 2/3 plus 3. And we'll simplify this down. We've got the 2/3 times 27, the 3 and the 27 here. 27 divided by 3 will give you a 9. So you really got 2 times 9, so you end up with 18, and I don't really need these parentheses, plus 27. I'm distributing the negative through, I've got negative 2/3. Negative times a positive makes this minus 3. And we can combine like terms. You have 18 plus 27, which gives you 45 minus 3 will give you 42. So you have 42 minus 2/3. Now these are like terms, don't leave it like this. They're like terms, they just don't have a common denominator. So to combine these, you need to find a least common denominator. For us, this is like 42 over 1, remember? So what you really want to do is multiply the numerator and denominator by 3 to get to the common denominator of 3. So 1 times 3 gives you 3 in the denominator. 42 times 3 will give you a 126 in the numerator. So 42 over 1 is rewritten as 126 over 3 minus the 2/3, which gives us 124 over 3. And that's the exact answer. You can leave it in the improper fraction form unless we ask you to convert it to a mixed number. That's okay. Right, so that was evaluating the definite integral. Remember, if it's a non-negative curve, this will give you the area under the curve. And the ones we did were all non-negative curves, but if I didn't ask you to find the area and just evaluate it, you just evaluate it. So in the next couple examples, which I'll do in the next video, we'll talk about some application type problems involving the definite integral.